Well, good morning. Thank you for coming to Mountain Lion Research Day, and I was hoping that you could migrate over to these round tables over here. And we actually have a SWAT team standing by in case it's necessary to sweep the room and push everybody in this direction. But I was hoping that I could introduce our first speaker, who is going to talk to us about a new initiative on campus that I'm excited about. Mountain Lion Research Day is all about a cross-campus conversation about the interesting things going on at UCCS. So thank you for coming, and you really can come this way. It's okay. I'll make sure. Dave, can you make sure no one steals the posters while people are walking to this side of the room? Thank you. And in order to promote research, we have a lot of departments with faculty and staff who are interested in doing research projects, but they don't have graduate students, but they do have lots of talented undergrads. So we've been thinking about a way of incorporating more undergrads into the research programs of faculty in every department and college across campus. So I'm going to introduce the person who is heading up this new initiative. It's Professor Rebecca Webb from Mechanical Engineering, and she's going to describe what this program is. And a lot of our departments have been doing a fantastic job of incorporating undergraduates in research, and she is working with them to find out best practices and export those to other faculty. We have colleges that are already putting some funds behind it, but we thought it would be worthwhile to centralize this activity in order so the students and the faculty could benefit. So you're going to come? Here she comes. Yes, thank you. Oh, and what did you do for the talent show in high school?
Gymnastics. Would anyone like me to do a handstand? Okay. Well, so good morning. I am Rebecca Webb from Mechanical Engineering, and I'm here today to talk about the Undergrad Research Academy. And a lot of you have already heard about it, because when you're as excited about a project as I am about this one, you'll talk to anyone who'll listen. So please bear with me. The idea with the Academy is that we would like to have undergrads work on meaningful research projects with faculty mentors. Through the program, we like to pay as many of the students working on these projects as possible. We also like to have them attend monthly research seminars as well as present their research at these seminars. In addition, we have them present their posters at Mountain Lion Research Day. The students that are involved typically are going to apply during their sophomore and junior year so that they'll be juniors and seniors when they're participating. Next year, we'll be looking for students with a 3.7 or above, and we'd like the students to have a faculty mentor. I just got louder. Okay. We'd like the students to have a faculty mentor identified to work with. So this year, we have our first class of undergrad researchers, and I'd like to announce them today, and most of them are here. So when I say your name, guys, if you could stand up or raise your hand so we can acknowledge you. This is a fabulous class, and I'm very excited about it. So from psychology, we have Jason Adams and Sandra Garcia, and they're around. From biology, Mary Rupp, Chris Ritchie, and I can't see my slides, I'm sorry, and Kim Huang. From engineering, we have Fraz Salim, Corbin Spells, Mario Arias, Chris Brown, and who did I say? Colin Curtis. From library, I always do this to Colin, I'm sorry, Colin. From library, Tawny Miser. And then from English, we have Olivia, I'm not even going to try to say your last name, and Sarah Horton. So we have a fabulous class, as you can see from my chart, which I had to add in because I am an engineer, that we were able to fund 9 of our 13 members. So we're very, very excited about that. And the reason that we were able to fund them is because of our very generous supporters. So first of all, the Office of Research and Innovation was able to give us 7 student stipends, which we're incredibly grateful for. The deans of LAS, engineering, and library also contributed student support, which was huge and very, very helpful. And finally, some of the PIs, including Jeremy and myself, kicked in a little extra to make sure this thing really went. So we're very grateful and thankful for the support and excited to start this year. If anyone has any questions, I'll be here all day, and I'm going to put in a much longer version of this presentation up on the website so you can see a little bit about every project and the student doing that project. So that should be up in a few weeks. So thank you very much and enjoy.
Hi, and I am Michael Larson. I'm the Associate Vice Chancellor for Research. I turned up the volume for Rebecca, but now it's too loud for me. The way we have this organized today, in addition to being a conversation about research that's presented on 106 posters behind you, we also have the morning punctuated with some presentations from faculty across campus. And then we have a keynote speaker that I think you'll find fascinating, and a special awards ceremony right before lunch. And everyone is invited to be here for a buffet lunch. And if you agree to participate again next year, we won't even charge you for the lunch today. It's free. Fine. So the first speaker of today is Joe Zhao, who's doing fantastic work in cloud computing. Everybody always wants to know what is the cloud all about? How does it work? How is it different from just having a mainframe server? And he was going to be here today, but unfortunately he ran into some difficulties late last night, so I had to find someone to fill in. So I'd like to introduce me. It's my event, so why can't I talk? So I wanted to talk to you about one of the projects I have going on that I'm very excited about. And I've done research in various areas, but recently I started looking at the effects of lasers on biological tissue. And I'm thinking about various things that might be helpful to people. And what I'm going to talk about is a surgical device that uses lasers to fuse tissue together as an alternative to sutures or staples. And I've proven this, that this can work in the lab, and found an application that I think will work well. I have invented another surgical stapler that dispenses bioabsorbable staples, and it's now being used by surgeons, and it's exciting for me to know that people are being helped by something. So this is another foray into that area. So I wanted to talk to you just very briefly, and I'll race through this, about some of the science behind closing wounds using lasers instead of having to stitch it together, and then an embodiment for this that's tailored for a particular kind of surgery that I hope will be able to help people. And here's a cartoon that shows a slab of tissue. So this is just a cross section, and inside the tissue, it's very inhomogeneous. We've got some constituents that scatter light. We've got others that will absorb light. And if we think about this slab being hit by a laser beam, some of that light bounces off the front surface. Some of it goes in and scatters around and comes back off as a glow. Other light will find its way right through the tissue and go through the other side. Most of you have probably at some point held a flashlight up to your fingers and noticed the red light that comes through the other side. So that's light that makes it all the way through. And what I'm interested in is the part of this light, the radiation, that gets absorbed by the chromophores, or constituents that are sensitive to the light inside the tissue. So where these photons are being absorbed will act like little sources of heat, and maybe we can use that heat to do something good. And if we just in general think about the effect of temperature on tissue, we can look at this little chart here that shows in general if you have between 0 and 40 degrees C, you'll warm the tissue and it'll feel nice and toasty on a cold day. But when you get past that, you begin to do structural things to the cells that you're hitting with the laser light. 40 to 60 degrees C, you begin to rupture membranes all the way up to eventually you'll burn tissue if you heat it large enough. And on this chart, we're interested in this zone of about 60 to 90 degrees C, because what we can do is denature the proteins in the connective tissue. And if you can think of how proteins are bonded together, how I like to think of it is you cook spaghetti, you pour it in the colander, and it's this mass of noodles all kind of stuck together. And if we think of the wrapped proteins that way, and they're held together by bonds that can be broken by heat. And so you don't take the protein apart, but you can break those bonds and allow the protein to stretch out. And as you cool it down, it'll coil back up. So if we do this across an interface, we can actually make the tissue a little gooey, and it'll stick up with other tissue across an interface. So that's the effect that we're looking for. And here's a little cartoon to try to show this. This is two pieces of tissue that we would bring together in a butt weld. You heat it up, and these proteins linking across the interface. And just to show you that this actually works, here is a real sample across an interface just like that we fuse together using lasers. And at least qualitative, you can look at that and think, wow, that looks pretty good. And it does work. The advantages of using lasers is you can do this wet or dry conditions. You get immediate closure, which is nice. With sutures, you have to stitch it together and then it heals over time. But here you're actually getting a watertight seal right away. Things seem to heal faster. There's no foreign body introduced, so nothing can be rejected. So it begs the question, if this is so good, how come people aren't already doing it? And we'll get to that in a second. Now, here's the part of the program. We are doing samples with real tissue. So if you want to look down at your table because you just don't want to see any. But here's a little slab of some skin. It's tissue that we're using to do some experiments. And we've got this lab set up with a laser where we bring two tissue slabs together and see if we can fuse them together. And in fact, we can. There's a specimen sitting in the middle. This red fiber optic cable comes from the bottom, and we use that to see if we can spot weld the tissue. And we indeed can. So this is that sample in the upper left that I just showed you. It's two layers stacked, one on top of the other. And right there is this little spot weld. And in the lower right is one of my students trying as hard as he can to pull those apart, and he just can't do it. Actually, that part's a lie, but it's the only lie I'll tell you. It does stick together, and it has fairly low tensile strength, but the tensile strength is recovered fairly fast. And actually, that's the reason we haven't seen this used in practice, because you have to find a situation where there isn't a lot of tensile strength that will just pull this bond apart as soon as you make it. So fortunately, I've hit upon a first application that I think will work. And there are a lot of things. One is if you just take a laser and you put it in a physician's hand and he or she heats up some tissue, by the time you actually affect the tissue by seeing a visual change, it's too late. You've already done too much damage. So we need some other way of gauging when enough is enough in order to do what we want to do. And something we have learned using different types of tissue is you have to tailor the laser characteristics, the wavelength, the dwell time, the power level to a particular tissue system. And so that's why there is no one-size-fits-all when it comes to using lasers to do this. And I'm going to start with a nasal device, in part because I'm well familiar with this procedure from that other stapler I mentioned. And it looks like a fairly straightforward path to getting the FDA to approve use, because they consider the inside of the nose to be part of the outside of your body. So no one is going to die if you punch a hole in their septum. They might whistle when they breathe, but that could have some benefits, right? So here we see somebody there in the front of their nose is lopped off, and inside the middle of your nose, you know, from looking at the poster of Pirates of the Caribbean, there's this bone in the midline of your nasal cavity, and there's cartilage in front of that wiggles here. And there are lots of procedures that require that you have to remove some of that bone and cartilage, septoplasties, rhinoplasties. Statistically speaking, there are many of you in this room who have had those procedures done, and you know that it's nasty to do. There are lots of reasons we have to do this. If I turn my head to the side and I cut off half of my face, this picture just shows the tip of the nose is on the left, right there, and then this is bone and cartilage up here. Wow, really magnifies there. So we're going to take out part of that cartilage and bone, and then we need to stitch together the skin flaps that cover both sides. You stick your finger up your nose, you feel skin on both sides. So what we're doing is actually taking the cartilage and bone out from under that. We have these two tissue layers, and we have to stitch them back together. Because if we don't, the cavity can fill with blood. The front of your nose starves the cartilage that's still there. It turns yellow and gets soft and sinks in, and the person's worse off than they were before. So we have to stitch it back together for lots of reasons that were listed there. So I have a movie here. And again, this shows, this is just a procedure. Somebody's nose is being worked on. And what you're looking at is stitching those two tissue flaps together, 7 centimeters back, going back and forth. This takes, I did an IRB study at a clinic. This takes 15 minutes of operating room time just to stitch the nose back up side to side, and nobody sees this work. So you just need to get it done, and nobody likes to do it. And if you don't do it, then tissue ligaments can bridge the gap, because when you're sending this little Keith needle back and forth, you nick the outside, scar tissue can form, and then you have to go and clear it up. So this is the device that we have in mind to use in order to make this procedure of closing that wound and tack welding those tissue layers together. It plugs into a laser. It has 2 arms to it and sticks up the nose. So in this almost realistic rendering, you see there's the cartilage and bone in between those 2 layers of skin. You stick this device up someone's nose after the procedure. You squeeze the handle together. It holds the tissue. The laser fires. It tack welds. It's preset how long and the power level, so you're not relying on the physician to have to know when to stop, and it sticks it together. And here's a picture up somebody's real nose showing the arms of this device and how it works. I'm working with some folks up at CSU. This is Jeremiah Easley, who is a surgical veterinarian who is doing some work with us. We've just been approved for doing our procedure on sheep, and you don't have to worry about the sheep, anything bad happening to them. All we're doing is giving them the best-looking nose in the whole sheep pen, so they're very proud of what they look like when they're done with the nose job. And everything is good, and we'll move on. So there's the product, and it currently is in this embodiment. We have a patent issued on this device, and so I'm hoping that someone's going to come along who is going to want to use this, because there are plenty of reasons, and I'll just skip through. You can trust me that it's good for the patient, it's good for the physicians, and we'll skip this. This was one of my volunteers. So I'll just end there and let you know that this has a big market worldwide. There are over 1 million cases a year that could use this device. And we have intellectual property, and there's a summary. So do you have any questions about this project? I know that was really fast, but it's near and dear to my heart. And if you ask one question, it would make me really happy. Thank you, Tom. The question is, why do I think there's a fast path through the FDA? And the FDA right now is kind of a broken system. It used to be that if you had a drug to develop, the average cost of a pharmaceutical was about $1.3 billion, which is crazy, and it takes years to get it through the FDA. But devices were a little different. Before 1978, in fact, your doctor could use anything he or she wanted on your body in the operating room, you know, the circular saw from the garage, whatever. So we left it up to their discretion. But all that changed in 78, and we started clamping down on devices that physicians are allowed to use, and they now need FDA approval. But that was because big things were coming online, like big MRI machines and things that could really hurt people, and we need to make sure they're checked out first. But smaller things like this, if we trust the physician to make that decision. But that has all changed just in the last 5 years with drug-eluting stents. So now what we have is devices are kind of merging with pharmaceuticals, and we have devices that include drugs that get released over time. So the FDA has really clamped down on devices too, and the cost has escalated to do human trials and such. But for this, as I mentioned, fortunately, the FDA looks at the nose as being part of the outside of the body. This is not a life-threatening kind of device. And the FDA likes to look for predicates that they can say, oh, we know that's safe, and this is kind of similar. And fortunately, the FDA is no longer afraid of lasers that have found application in ablation and other uses, if anybody's had retinal detachments. So they feel more comfortable with a laser-based device. So I visited the FDA, I've kind of run this by them, and they feel comfortable with it. And so it looks like we ought to be able to get approval with a fairly small sample of people. But with the government, you never know. Yes? Right. Yeah, this is a good first application that I like because of the quick FDA path to approval, but I think the real payoff is if we can exploit that trait of the watertight seal that is potentially achievable for gastrointestinal surgeries. Leakage from one place to another can be deadly. And if you have a connection with either sutures or staples, it's a point-to-point connection with no continuous seam, and we just hope the whole thing holds together. And here the promise is if we can get a complete seam like a Ziploc bag, then the chances of that leaking from one place to another would be greatly reduced. The issue there is it's not a short path to FDA approval if we want to start doing surgery on anything in the abdominal cavity. So we're going to start here and hopefully build some confidence and see how that takes off. So any other questions? Well, thank you for humoring me. I'm sorry that Joe wasn't here. You may have liked him better, but fortunately for me, you'll never know for sure. So if you want to go back and enjoy the posters and ask people questions, that's what today is all about. Thank you. So our next speaker is Professor Rex Welshon, who's our Associate Dean in the Liberal Arts and Sciences, and is also a professor of philosophy. And I enjoy talking to Rex. He has a very broad perspective on a lot of topics. And one area that he is particularly interested in is what makes you, you. So Tom, what makes you, you? You know, if we cut off Tom's ear, he's still Tom, right? But if we keep doing that, at some point we say this isn't Tom anymore. And there's a physiological component to that, but there is also a mind part of that that I have a hard time getting my head around. But Rex has all those questions worked out perfectly. So if you would please welcome Rex Welshon. Oh. And you will notice that he doesn't use PowerPoint like a crutch, like I did to divert your attention somewhere else. And I like that.
Thank you very much, Michael. I'm going to talk to you today a little bit about how a philosopher gets interested in the phenomenon of consciousness. Philosophy is a very peculiar discipline. Most students who take a philosophy class for the first time are kind of befuddled by what's happening in the classroom. The professor is talking and talking and talking, and the professor is talking about something, but it's usually not clear to the first-year philosophy student just what the philosophy professor is talking about and why the philosophy professor is making so much fuss about the meanings of words. Philosophy is a meta-level discipline. It looks at the product of science and asks questions about that product. Philosophy also has a standard set of issues that it focuses on. For example, it focuses on the nature of truth. It focuses on the nature of the mind. It focuses on the nature of the good and of justice. It focuses on the nature of beauty. These standard philosophical topics have been discussed across all cultures as long as people have been talking in an intellectual way. They're talked about in the Occidental history of Western culture. They're talked about in Buddhism. They're talked about in Hinduism. They're talked about in Islam. All of these cultures focus on these great perennial questions. Philosophy has always been the repository for some of the best thinking about these issues. What's happening right now in the philosophy of mind is unprecedented. Philosophy has, for centuries, proceeded along its own path in a kind of a priori way, just reflecting on the nature of the mind and attributing to our mind certain properties and certain qualities that it then challenges science to provide a physical basis for. Until 20 years ago, philosophy was fairly comfortable in assuming that none of the advances of science, psychology, cognitive science, behaviorism, any of these sciences, would ever really tap into the nature of the mind. Because there are these peculiar facets of the mind that seem recalcitrant to scientific investigation. Its interiority, for example, the fact that my mind is my mind, the fact that I am me and not somebody else, the fact that all of my conscious experience has a particular qualitative character. There's a way it feels like to be me. There's a way it feels like to see black. There's a way it feels like to smell caramel. There's a way it feels like to hear a bird singing in a canyon. All of these are peculiar facets of the mind. Historically, certain branches of psychology have taken on the project of trying to understand these peculiar facets of the mind. But they've been routinely bad science. If you think of behaviorism, behaviorism started off with the idea that the only thing that was relevant for psychology was overt motor behavior. But if the only thing that's relevant for psychology is overt motor behavior, then everything that happens up here inside our skull is written out of the relevant domain of psychology. That view of behaviorism didn't last very long because it was so obviously inadequate. But then the behaviorists started to enrich what psychology could talk about by talking about dispositions to behave. And it started talking about internal variables. All of that became clear in the late 1950s as necessary amendments to behaviorism if behaviorism was going to have any hope of understanding what we do when we think, when we feel, when we hope, when we love, when we lust after somebody. All of those are interior experiences that have overt motor behavior outcomes, but they are interior as well. When it became clear that behaviorism failed in its ability to explain human psychology, another paradigm, to use a bad word, was needed, and that paradigm was, of course, computer science. Cognitive science as a discipline grew up in the shadow of the advances in computationalism. And from the 60s through the mid-90s, computationalism as a overarching framework dominated philosophy, it dominated psychology, and it dominated the incipient science of neuroscience. But even computer science, as great as it is, cannot provide an analysis of the qualitative character of conscious experience. Cognitive science made huge advances in understanding what our thinking is like, what it is to process information through a brain. It made huge advances. But there were these recalcitrant philosophical issues. Again, as in the case of behaviorism, the computationalist cognitive scientists said, oh, these weird philosophical properties, we don't need to worry about them at all. They're going to be written out in a complete psychology. But if you think about what is being written out when we write out the qualitative character of experience, the subjective perspectivity of experience, you're writing out quite a bit. But there was no room for it within computationalism. There's no algorithm for the taste of vanilla ice cream. And so these weird philosophical properties were admitted to exist, and it was thought that further advances in cognitive science that was based on computationalism might provide the space for understanding them. But it became clear that it would never do so. These qualitative characters of conscious experience, the fact that it's subjectively perspectival, and the fact that our experience is about something else than itself, we're not just locked in our brains, whirling around in our own brains, our thoughts are about things in the world. These properties, although they could not be discussed in a computational framework, continued to invigorate the philosophers in thinking that there was something that cognitive science wasn't yet catching. And then, in the 90s, late 80s actually, new technologies suddenly emerged. fMRI, PET, and all of the imaging technology of contemporary neuroscience. These machines suddenly gave us a real-time view into the workings of the brain as it was doing what it's doing. When that occurred, the black box of the mind was suddenly opened, and you could actually see inside these black boxes of a functionalist or a computationalist understanding of the mind. If you think about computationalism in the broadest sense, it's a set of input-output functions. You put in a kind of stuff, perceptual stuff, you go into the black box of the brain, and what comes out is perceptual experience. Until these imaging technologies were developed, we really couldn't see very well into the brain. There was a great deal of very good neuroanatomy. There was a great deal of very specific kinds of neuroscientific investigations into particular pathways in the hippocampus, for example. But there wasn't anything that provided us with systematic understanding of the brain in action. fMRI, PET, EEG, and all of the other technologies that have come on in the last 20 years have fundamentally changed brain research. And if you heard yesterday, President Obama has now announced a $100 million project for mapping the brain. It's going to be the cranial counterpart to the Human Genome Project. That's where philosophy comes in again. Within the last 20 years, all of these peculiar properties that scientists, psychologists have dismissed are suddenly the rage for understanding the brain. And there are dozens of research papers every year focusing on obscure topics like the subjective perspectivity of egocentric experience. And what these papers are doing is finding the neural correlates for these peculiar philosophical properties. There is an entire body of research in the last 20 years on the neural correlates of each of these sensory modalities. We now know the neural route of odor. We know that it's significantly different than the neural route of any of the other senses. Odor, unlike all of the other senses, roots primarily directly from the olfactory center in the brain, directly into the prefrontal cortex. It typically does not go through the thalamus. There isn't this pre-translation device necessary as there is for vision, for hearing, for touch, and for taste. All of those have massive bundles that go from the distal sensory organs into the thalamus, and then from the thalamus into regions of the brain. Odor doesn't do that. It goes straight from the olfactory bulb right up into your brain. That's why odors code so strongly in memory. Odors and hearing can code incredibly strongly in memory, better than visual memories. We probably all remember the sound of the voice of a long-lost friend, somebody we can't see anymore and haven't seen in years, but we can still remember how they talked. We can remember how our fifth-grade teacher talked. These are remarkable discoveries. However, the philosopher, being the gadfly that she is still not satisfied. And that's where the kind of work that I do comes in. Philosophers are by nature argumentative. That is what we do. When I do work, I am interested in the argument for a conclusion. Bertrand Russell once said that philosophy is a discipline where you start with a premise that nobody doubts and derive a conclusion that nobody can believe. That's more or less right. Philosophers are always taking what other people say and subjecting what they say to criticism. The philosopher, perhaps in a self-delusional state, thinks that by doing this, knowledge is pushed forward. Most of the time, people listen to the philosopher and then say, "Thank you very much," and go back to their labs and continue to do their work. But every once in a while, a philosopher will actually say something that's important. And all research shares that property. Most of our research that we do, no matter what field we're in, advances the field in some minor way. Every once in a while, one of us will be lucky enough or enough of a genius to find out what's wrong with an entire branch of research and redirect it in a fundamentally new way. That's what we all do as researchers. We are interested in pushing knowledge forward in the kind of workmanlike way that science typically proceeds. And every once in a while, somebody makes a fundamental discovery that reorients entire research paradigms and programs. I'm not going to make any kinds of pretensions about my own work. My own work is in the workmanlike category. I'm interested in a very particular set of issues. And the issues that I'm interested in are the neural correlates and substrates for the egocentric perspectivity of conscious experience. Now, that's a bunch of fancy-sounding words. And there's a lot of fantastic work being done on this area. We now know that the parietal region, the interparietal sulcus region, is responsible for, under rights, is the substrate for our egocentric map of the world and our position in that world. It is in the interparietal sulcus that the perspectivity of visual experience, and by extension all experience, first gets developed. It's not where it gets finished, but it's where it first gets developed. If you lesion bundles out of the interparietal sulcus, you get predictable neuropsychological disorders. And these predictable neuropsychological disorders go to severe dysfunction in the ability of a victim to be able to locate themselves in space. So we know that activity there is necessary for, not sufficient for, but necessary for our egocentric experience. If it doesn't work properly, you don't get that experience, that kind of experience. But even if it does work properly, the interparietal sulcus region, even if it does work properly, you can have other dysfunctions elsewhere in the brain that also result in a neuropsychological disorder of a failure to put yourself in space. So what we're learning about the nature of the brain is that it's an incredibly complicated, emergent, interconnected, dynamic system. There are massive feedback loops in the brain. There are massive feed-forward loops. They work together in a number of different ways. All of that's now relevant for philosophy in a way that it's never been before. Philosophy used to just proceed on its own argumentative path, more or less happy with whatever science said, knowing that whatever science said was not going to be able to touch the philosophical properties of consciousness that we take to be essential to the nature of our experience. But that's no longer true. Philosophy of mind that does not take contemporary neuroscience into account is now a dinosaur. And the vast majority of philosophers of mind who are still interested in these topics are now working very closely with neuroscientists in group projects to try to isolate the neural correlates and substrates of these philosophically introduced properties of consciousness. I think the future is extremely bright, both for neuroscience, neuropsychology, the imaging movement, the brain mapping movement, and for philosophy of mind. Because some of the problems that have been problems for everybody for 2,000 years, they won't be answered in my lifetime, but we now know how to go forward in a way that I don't think we've ever known before. And that makes me really excited. Now, of course, in conclusion, I can say there's some people who are deeply dissatisfied with this kind of work. If you have a religious assumption that consciousness is a gift from God, then no amount of science is ever going to be able to explain consciousness. If you think that your soul, your conscious soul, is somehow distinct from your brain and your central nervous system, then you're never going to be satisfied with this work. Because this work is all based on the assumption that we can identify the neural correlates and neural substrates of conscious activity. But if you think that your soul is somehow unique, distinct, separate somehow from your body, then this kind of work is going to be deeply dissatisfying, even disturbing. But where's the appropriate place to bring that up? Well, it's philosophy classroom. That's where we entertain those kinds of objections. And so even as this chain of research shows enormous promise, there will still be resistant philosophers and resistant individuals who really don't like this work. And they will continue to offer arguments that will start from premises that nobody denies, and they will end up deriving conclusions that nobody can believe. That's the nature of philosophy. I think it's the nature of research in general. It's where we're headed with brain research, but know that always, wherever the advances are made, there are going to be gadflies. And those gadflies are going to be moved by the inadequacy of a science to capture what that person thinks is unique about that particular phenomenon. And that's where philosophy resides. Thank you.
All right, we're going to introduce the next speaker. Did I say that already? So come on over close to the platform where he'll be able to see you. And I'll introduce Patrick McGuire. He's a professor in our College of Education, and he's doing some innovative things with STEM education. And so I asked him to come and talk about some of the research he's doing on how modes of transmitting information affect students, their desire to participate, particularly science and technology. And he is featured in our research magazine. And I was hoping we had some copies of those. And if you haven't picked up the Innovations magazine, it's in its fourth printing, coming up on number 5, where we feature some of the good work going on at UCCS, and Patrick is one of those that has been featured. And without further ado, I'll introduce Dr. Patrick McGuire.
All right, thank you. Unfortunately, I don't have any turtle jokes or anything to start off my presentation with, but hopefully I want to spend I want to spend a few minutes today talking with all of you about some of my work that I've done really the past 5 or 6 years, focusing on the area of math and science teaching and learning, particularly at the preschool level, which a lot of times is often neglected in terms of that subject, and a lot of teachers tend to gravitate more towards the language and literacy and those types of subjects, and really tend to neglect this really critical area of math and science. So what I want to do really is talk to you about 2 different parts of this investment in early childhood education. Starting off talking a little bit about why we're spending so much time doing this type of research, and then also how we're supporting teachers and students in this area. So I want to start off with a little pop quiz. And so there's been a lot of survey research and talking about school readiness for kindergarten level students. And before we get started on this talk, I want you to take a minute at your tables and see if you can answer this question. According to recent research, approximately blank percent of 5-year-olds, and that's traditionally the age when students enter kindergarten, in the U.S. are not academically prepared to start school. Okay, so A, who thinks it's A? B, 50%, C, 66, or D, 75? Okay, so I saw the majority of hands. It looks like C or D was your answer. And based off a recent survey of about 500 teachers across the United States, their research has shown that approximately 2/3 of kindergarten students enter the classroom not adequately prepared to start school. And that's, to me, that's a really concerning number, thinking about 2/3 of students entering the kindergarten classroom really not ready to learn. And so that's a huge issue right now in our country. So why is that such a problem, or why is that even a concern in our country? And shouldn't kindergarten really be the first time that students start to learn this formal type of, these formal subjects? Well, there's other research that really shows how powerful that early investment in early childhood education can be. And the returns on that investment, the estimates are anywhere from 8-to-1 to 16-to-1. So what that means is for every dollar that's spent on preschool level programs and intervention, it pays society back anywhere from 8 to 16 times. And that graph really demonstrates that as kids start to get older, the investment return actually goes down, and at some point it becomes negative. And so if you wait until elementary school and then high school and beyond, dumping that money in, it's still important and it's still helpful, but you don't get that same bang for your buck if you wait later. And so really that early intervention is so important in the classroom. Okay, so in my talk, I want to talk a little bit about, in particular, why children need math and science skills specifically. And so, well, the first thing is, a lot of people say, well, shouldn't kindergarten and pre-K, shouldn't that be a time for kids to be kids? Shouldn't they just get a chance to play and socialize? And all of those things are important, and I'm not up here saying that we should make everyone a little mathematician and scientist. But there's research that shows that children have a lot of informal math and science knowledge, and they even manifest that knowledge through play. There was a study at the Teachers College at Columbia where all they did was went out on a playground and videotaped kids, and 50% of their time was spent engaging in some sort of mathematical or scientific thought. And so kids are kind of naturally demonstrating this informal curiosity and informal knowledge. The second thing is, in particular for children who are at risk for school failure, achievement gaps are visible starting as early as age 3 and 4. And so this early intervention, the earlier we can kind of work with those students, the more of a chance we have to get them on the right path. And then the last thing is early math and science skills, starting as early as age 3, 4, 5, are highly predictive of students' later academic success. There was an interesting study at Northwestern University actually showing that math and science skills are more highly predictive of later reading skills even than reading skills are, which is kind of not an intuitive thought, but a really interesting finding, just showing how powerful those predictive variables can be. Okay, so that's kind of from the student perspective why we're focusing on this. But thinking about, why do pre-K teachers or caregivers need to really understand mathematics and science and how that looks with instruction? Well, the first thing is there are several validated curricula lesson plans, textbooks, things like that designed to provide teachers with ideas for activities. But simply giving teachers those types of things isn't necessarily the solution. Really, the main reason for that is that many preschool teachers, I kind of alluded to this at the beginning, tend to lack the confidence or the content knowledge to really understand how to teach at a high level. And so, so what's the solution? I mean, this is obviously a problem. We have lots of students coming into preschool and kindergarten classrooms really not demonstrating the knowledge that they need to be successful for later learning. About 5 or 6 years ago, I started working on a project at the University of Virginia called the My Teaching Partner Project. And some of you may have heard of other My Teaching Partner projects. There's actually a language and literacy one done about 10 years ago, and the follow-up one was the My Teaching Partner Math and Science Project. And what I want to do now is just to give you a little bit of context about what this project does. I want to show a short video. It's about 5 minutes, and it really gives you kind of a nice overview of what we did with this project. Okay, so hopefully that video, I was kind of deciding whether or not I wanted to actually show you the website and go online, but I thought the video was a nice kind of way to give you more of a big picture overview of what we did in that project. So for the rest of my time, I want to talk a little bit about some of the research associated with this project. This project is actually still going on. It was just funded by another round through the Institute of Education Sciences. When I worked on it, it was a Goal 1 project, and now it's a Goal 2. So anyway, they received another really nice grant to keep this work going and hopefully expand to more classrooms. But really, there's two main research questions that drove our work for this project. And the first one was really just thinking about the curricula. Did providing the teachers with these curricula, did that A, improve student outcomes, and how did that affect the quality of the classroom teaching? The second thing, and the second piece, is looking at the actual teacher supports. And so those online, the video-based types of things that you saw in that clip, what effect did those have on, again, A, student outcomes, and B, teaching quality? So the most recent study, and we're still finalizing our data. We've done the majority of the analysis at this point, and we're starting to write up some of these papers. It was done with 35 classrooms across the state of Virginia, and we used a randomized control trial for 3 different groups. We had a business as usual group. We had a group of teachers that just received our curricula, and so that means they got all the lesson plans and materials. And then we had a third group who received everything. They got the materials, they had all of the online supports, and then they also had some professional development support as well. So these are just kind of the ways that we assess student learning. There was really a lot of assessment that occurred throughout this project. We used some validated assessment measures to look at student growth in mathematics, namely the team of 3, and a subset of that test for geometry and measurement. Interestingly enough, there are no validated instruments that really measure preschool level science, and so we had to develop our own in-house measures to really get at that data. For teacher ratings, we actually had the teachers also evaluate their students using formative assessment kind of checklists, where the teacher was responsible for, as they were working in students in center time or small group, they assigned a number of 1 to 3 to really demonstrate the proficiency of their students. And these are the ways that we assess the quality of the classroom teacher. We looked at fidelity, so how consistent they were with implementing the lessons as we had written them. We also looked at dosage to see how many of the activities teachers implemented. And finally, we used the classroom assessment scoring system as kind of our main model of looking at teaching quality. Okay, so some of our results from this. And I know just kind of for the interest of time, we don't have time to go into all of these results, and maybe in kind of the Q&A we can address some more specific questions. But the MTPMS, the plus group, basically the group that received everything, as you probably would have predicted, the children in that group, the children in those classrooms showed the most significant gains in math, in particular in the areas of geometry and measurement, and also in science, in particular the area of life science. And those teachers in the plus group also had higher class scores on average. And all of this obviously is compared to the teachers who were either in the business as usual group or in the group that just received the curricula. Okay, so some of the implications of this work, kind of as I alluded to earlier, I think what our work shows using that three-tiered design for our randomized control trial, that just providing classroom teachers with resources, especially in math and science, isn't necessarily enough, that we need to also provide that embedded professional development piece. And for more information on this project, we have a website. It's mtpmathscience.net. You can see some of the video demonstrations and things like that. And it also has a link to some of the research papers that we're writing based off of this work. Like I said, there's more and more research underway and kind of spin-off research for this big grant. And if you have specific questions for me based off this talk or some of the things that I'm doing associated with this project, I have my UCCS email up there for you. Okay. Thank you.
All right, thanks again for coming out. And even though we have some people still in line, we'll wait to introduce our keynote speaker until they're able to sit down and join us. But in the meantime, we have a very special presentation to make. And I'm going to introduce Tom Smurden, who is the director of our Technology Transfer Office. And in the CU system, there's a centralized office. There are representatives for each campus. And what they do is facilitate taking inventions from UCCS and translating those into commercial products, commercial services, in order to be able to improve people's lots in a commercial way. So I'm going to introduce the director of that office. But as it turns out, and I thought I would make up a story about him. And as it turns out, Tom and I were both undergraduates back in the day. And I remember clearly the day I saw Tom ride up to the academic building on a brand new shiny red bike. And I said, "Wow, Tom, great wheels." And he said, "Yeah, you'll never believe how I got this thing. I was walking to class the way I always do, and this woman rides up on this bike, and she hopped off, and she took off all of her clothes, and she said, 'Take what you want.'" And I said, "Good choice, Tom. I bet the clothes wouldn't have even fit you." So, all right, next time I'll make up a different story. All right, so I'll introduce Tom Smurden, the Director of Technology Transfer.
Yeah. Thanks, Michael. You know, your memory is a lot better than mine is about that. Well, it's great to be here. I'm actually the interim associate VP for Tech Transfer for the CU system, and as Michael said, what we do is manage the inventions that are disclosed to our office, and that involves evaluating the technologies and patenting them where that's appropriate. And ultimately and hopefully licensing those to companies for commercial development, either via an established company or a startup company. Now, in the past, we have had an annual awards event where we've recognized inventors, including Inventors of the Year from the various campuses. And this year we've decided to go to a campus level recognition. And and this is a perfect event for that because this is a celebration of the research enterprise and university researchers, and that is the source of the invention disclosures that we receive, the technologies that we see, and that really is the lifeblood of the Technology Transfer Office. So to present this year's Inventor of the Year Award for Colorado Springs is the Senior Director for Tech Transfer for the Boulder and Colorado Springs campuses, Kate Tallman. Kate.
All right, thank you, Tom. Thanks very much. And I've really enjoyed looking at all the posters and seeing what might be coming towards our office over the next couple of months. And I'll be here for lunch and circulating among the posters if anybody has any questions about technology transfer. I get down here about once a month. I'm happy to meet with anyone and answer your questions while I'm here. The Inventor of the Year this year for University of Colorado, Colorado Springs, it's long overdue recognition. Bob Camley has been named on 25 invention disclosures, and in fact, it's 26 because I got one just this week, since 2002. He's on 1 issued patent, 3 pending patent applications, and he was also on many applications with a collaborator, his biology collaborations in the past. You've been on 14 U.S. and international patent applications, and what's most interesting about Bob is who here has not collaborated with Bob Camley? He seems to be collaborating with every inventive person on campus. The subject matter of his inventions span 8 different categories in our database, all the way from therapeutic drugs to electronics. So he is truly a Renaissance man inventor, and I'm very glad to recognize him as Inventor of the Year. There you go.
And now to introduce our keynote speaker, I'd like to yield the podium to Dr. Kelly Klebe, who is the Dean of our graduate school and a professor in our psychology department. And I will sing her praises. She's doing a great job with the graduate program, which really is the heart of our research enterprise at UCCS, and I appreciate all she's doing. So take it away, Kelly.
So before I introduce Jesse Smith, our keynote speaker, I also want to talk about the Graduate School Travel Awards. This year is the first year that we've ever given Graduate School Travel Awards, and we gave 22 graduate students across 3 colleges and in 9 departments up to $300 to go to a conference where they were presenting research or for professional development, and we invited some to come today. So if those graduate students who got a travel award would stand up and be recognized, I'll read the names of people who I thought were here. But in the College of Education, so all of you can stand up, we have Sarah, Elsie, Grant Clayton, Helen Larman, Susan Jones, Nancy Hernandez, Dion Kobaski, Josh Hendrickson, Arjun Bala, Colin Mahoney. Those last 4 were from LAS. And from the College of Engineering and Applied Science, Yampi Gio. And so congratulations to all of you. Thanks for your work. You know, I see a lot of graduate students and a lot of undergraduate students here. So graduate students are doing research, undergraduate research students are doing research. I think we have a lot to be proud of that we get our students participating in these events. So if you're a student right now, graduate or undergraduate, will you stand up and be recognized as well? And let me thank you for your work. That should be a lot of you. All right. So I have the pleasure of introducing Dr. Jesse Smith as our keynote speaker today. You can see her title. Dr. Smith was an undergraduate here from 1993 to 1997, and she did her honors project, her research project with me, which was a pleasure. So I have fond memories of her for the past 15, 16 years from when, in order to maximize my research, my travel dollars, we went to a grant in Tennessee together. So we flew into Georgia because it'd be cheaper and took a road trip. So I made Jesse eat boiled peanuts and other savory appetizers. So because we were in a different place studying different things. And we are still working together. So we're collaborating together on different kinds of projects now. So this undergraduate research academy that we're launching today and that it's starting, I think is an important development for UCCS. It's an important influence for students, but it's also an important influence for faculty. This has been a very positive collaboration for me. I can't speak to what Jesse has thought about it, but it has been an important relationship and that it's gone for 15 years. So I'm happy that we're here to kind of help promote the Undergraduate Research Academy that's being started today. So Dr. Smith received her BA in psychology in 1997. She went on to the University of Utah and received her PhD. She's currently Associate Professor of Psychology at Montana State University. She's also the Special Assistant to the Provost Director of ADVANCE. ADVANCE is a program that helps think about how to promote women in STEM fields, so, and her research is directly related to that. So her research interests span 3 areas: intrinsic motivation, goals, and stereotype processes, particularly as they relate to gender and achievement. So her research emphasizes the role gender, ethnicity, and sexual orientation play in understanding both the perceiver's standpoint, application of stereotypes, and the target's experience. How does it feel to be the victim of a stereotype? So for example, she developed a stereotyped task engagement process model to better understand how cultural factors, such as gender stereotypes, and individual factors, such as interpersonal orientation, produce a person-environment match or mismatch that influences motivation, performance, processes, and outcomes in stereotype domains, such as computer science. Dr. Smith's research is grounded in experimental methodology and has been applied to educational, political, and health-related domains. Her research is currently supported with funding from National Science Foundation and the National Institutes of Health. She's going to speak to us today on lab rats, the value of undergraduate research experience from a personal and empirical perspective. Help me welcome Dr. Smith back to UCCS.
Yes, thank you. It's great to be back, and I do not recognize this campus. When I was here, there wasn't even a dormitory on campus. They were just being built, so it's incredible to be back, and I would be lost if you just plopped me down in the middle. I could probably still find Main Hall, and that's about it. I want to start by asking you about the culture of science and research, and of course, whenever I have a question now and I want to Google it, because that's a verb, this is a little app. This is a screenshot from my phone. And you know what's really nice about Google is it just anticipates what you want to type in. So I started typing, and I said, scientists are, and it wanted to fill in the blank for me as to what the top hits were. So here we go. Scientists are atheists, are from Mars, are evil, are the new rock stars. So it wasn't until the very bottom that I started getting interested in that. So this is what Google says is the stereotype. What are scientists? Who are they? And this is what comes up in terms of top searches. And so I want to talk about what is science research? What do we think about when we think of a scientific researcher? What comes to mind, and what are those stereotypes? And what you can see here on the screen is a long time ago, back in the early 80s, they replicated this again in the late 90s. They asked children, middle school age kids, to draw a scientist. It's called the Draw a Scientist test. And just give them a piece of paper, draw a scientist, and this is what they draw. And what you can see is that it's a crazy white guy with funky hair, and a lab coat all by himself. And this is this image that people have of scientists, that kids had of scientists, that now dates back almost 20 years. And we've recently replicated this at Montana State and got similar findings. So the stereotype of who is a scientist still hangs on, even though there's lots of diversity within science. And if you think about the major sort of image of science of somebody in a lab coat, there's something fundamental. If you're a researcher, you better be wearing a lab coat. And there's going to be a microscope involved and some beakers. And of course, that's very certainly true. That is part of science, but it's a very narrow definition. And there's a lot of other things sort of involved here, because if you don't sort of identify it as a crazy-haired, lab coat-wearing, lonely guy, science might not seem like a place that you would fit in. So science gets a bad rap. There's a stereotype about what scientists do and who they are. The joke is that even the rat in science is white, the little lab rat that gets tested. So we have to sort of think about if we really are interested in getting more people, and I'd say we are, these are just cutouts from the headline, into science, technology, engineering, and math. Both men and women. We just need more people. The United States needs more people who are interested in these fields because these images of science probably don't appeal to really very few people at all. And so if we have this goal to get more people interested in science, and of course one argues, well, if we have a big slice of our population in underrepresented minorities and women who are even more unlikely to want to go into science, then we have a sort of an untapped population of people that we might want to reach out to. And where's the place to do that? At the university, right? Where we're surrounded with faculty and other students and graduate students who are doing research. This is the place in which we might be able to combat some of those stereotypes about STEM. So in my own research, we have this is my NIH-funded project. We call it Project CURE. It stands for the Culture of Undergraduate Research Experiences. And we have gone in and we have done investigations, research on research assistants to find out what are they doing in these labs with the faculty mentors, what kind of things they're doing. And I can tell you that the number one thing they say that they do with their faculty mentors is dishes. They are washing dishes. And there's no gender difference there. Everybody's equally cleaning up after the lab supplies. But then after that, you see some real interesting distinctions. And so these women and underrepresented minorities, even when they're very qualified, so these are gifted students who say that they've got good grades, they've taken the SATs, they've gotten good scores. These are not unqualified students, but they are choosing to go through their major. They sort of, over time, decide that it's not for them, even when they acknowledge they're getting good grades. And it's very counterintuitive. And for a lot of years, most people doing research on these kinds of phenomena have just thought, well, it's about self-efficacy, it's about confidence, it's about skills. And if we just tutor the heck out of these students, then surely they'll come around. And that is important. That is a necessary thing that we need to do. And we need to keep those support structures in place. But the issue, of course, is even the ones who are really good don't seem to be that interested. And so our project is meant to look at these students who are undergraduate research assistants. So they've already sort of passed a bar. They're science and STEM majors, and they've gone and started working in a faculty lab. So they've already really made it a long way in the pipeline. They've made it to about their junior year at least. And so we can follow them over time. We follow them for 4 years to see, are they going to graduate school? Are they going into industry? Do they graduate? All these kinds of great questions. So it's a really important applied sort of issue. But we're also really getting an understanding as a motivational researcher in terms of what feeds into what people are interested in. There is, yes, what you're interested in is often what you're good at. But a lot of us are good at stuff that we're not very interested in. And I am really interested in a lot of stuff I am no good at. Right? So it is important from an interest development perspective to think about these questions. And our theoretical framework is what we call goal congruity theory. And this perspective is pretty simple. It's very intuitive. It says that you, as a person, as an individual, you have values, things that are important to you. And of course, we can talk about where those come from. But you value certain things. And if you're going to be drawn to situations or tasks or jobs and careers that fulfill those values for you. And so we use this notion to say, okay, maybe there's something about people's stereotypes or beliefs about what kind of values STEM has. What does science research value? And maybe that's turning off a whole group of students from pursuing STEM as a career. And I'm going to be very clear right now. I think it's erroneous. I think this is a stereotype about STEM. I don't think it's true at all. But it's again, draw a scientist, right? It's what your automatic beliefs come about. So STEM career provides opportunities to fulfill certain goals, but if you think that those aren't the goals that you have, you might not be interested. So our hypothesis is that certain groups of students are underrepresented in STEM because they especially value certain goals that they don't think STEM is meeting, even though STEM arguably really could meet those goals and if they had some assistance from their faculty mentors, which will be my take-home point here. So what is the stereotype of STEM? Yes, okay, draw a scientist. We saw what it physically looks like. It has this stereotype as being very individualistic, and by that I also term as agentic. So this notion of you're by yourself, you have these aha moments, it's about prestige and autonomy and the freedom to I want to problem solve and just answer questions. It's related to things and not people. You hear people say, well, I'm more of a people person, and so STEM doesn't appeal to me. And there's a real emphasis on those journal articles and those inventions and those patents and things like that that seems very prestigious, and ownership is all about me. And of course, this lone scientist stereotype that they're involved in their lab all by themselves, wearing their lab coat, keeping their clothes clean, but they're alone. And of course, that's simply not true, right? We all have collaborators, right? Most journal articles have multiple authors on them. You're mentoring students. You're working with your other grad students and undergraduate students. And so there's actually it's a very unfortunate stereotype that STEM has, because according to goal congruency, if the stereotype of what science research is it's very agentic, and we have most people, men and women alike, really value working with others. And they want to know that at some level, what I'm doing has implications for something. So this is a communal value. And so what we're thinking is maybe what we need to do is help STEM sort of get the reputation it deserves as collaborative, as involving working with others, as coming up with engineering products and scientific discoveries that really can help somebody. Maybe you personally, maybe it's 10 steps removed, but it has those implications. So certain groups on average do more value these communal goals than others. But again, my research shows, and others too, that both men and women, both minorities and non-minorities alike, tend to really gravitate towards tasks that they think will fulfill those goals. So we have this notion of, if people don't think that STEM fulfills communal values, but it's more agentic in nature, and you value communion, then you might opt out. And unfortunately, in our curriculum, right, in a lot of the undergraduate classes that you might take, it's not until you're a senior that you get to take the good stuff. Right? It's in the first few years, you're memorizing equations, understandably, and definitions, and doing really this important foundation work, and we don't want to get rid of that. But if a student has to hang on for 3 years before they get any sense of why am I doing this, that could be problematic. So what we have found is that from the literature, if you take a description, a day in the life of a scientist, this was a really good study, and they manipulated the day in the life of the scientist to where he's all by himself in a lab, and he writes some emails, and he does some protein quantification tasks, and does all these things. Or they talk about mentoring the students and working with other people and having collaborations. Students were much more drawn to science if they had read this collaborative nature. So involving other people, if you can, to the extent that people believe science involves working with others, they report higher interest in pursuing those fields. Working with others, not just involving others, but actually getting to be side by side with your team. We all have research teams. It's very rare and almost odd to think of the person who's all by themselves doing their science. Helping others, if they think there's some applied sort of implication, seems to increase interest in science as well. Most of this is correlational, though, right? So you ask people, what do you think about science, and what is your interest in going into it? And most of the people then, it's all on correlation. So it's a survey study. We wanted to know, could we make predictions from a student's early experience in their research lab with their faculty member as a junior all the way out 4 years later, so we could actually make predictions over time. So this is research on doing research. And we have experimentally manipulated some pilot studies, and I thought I would just share one of those with you because it's we're only 2 years into that longitudinal project, so I have some data on it. But this is pretty easy to see. And if you're a faculty mentor or you're a graduate student, maybe getting ready to defend his or her thesis very soon, think about how you might change your discussion section just a little bit. In line with these results. So what we did is we gave undergraduate students at 2 different universities some descriptions, and we wanted to test does seeing communal connections of the scientific project help promote scientific interest, identity, intentions to go to graduate school, actual graduate school applications. We asked a lot of different questions. And does it help URMs in particular, or in women? But really, all sort of science students, would lots of people be drawn to these descriptions? We have several different studies. I'm only going to talk about study 1 here, but you can sort of see the progression. So if we can control for those agentic beliefs, because those are fun too. Everybody, it's great to have prestige and money and have autonomy. So we don't want to say get rid of agentic values. Absolutely not. We're just saying we might want to add on these communal goals as well. So here's what we did. Does providing communal information about your research increase students' interest in going into research? And what we took, it was the National Science Foundation puts out, I went to a conference and they put out this beautiful glossy colored, very well put together sort of example of all the research they've been funding through the years and for that particular year. So this was last year's brochure came to me and I'm flipping through it. And some of these little descriptions spent a long time talking about how the team that they worked with, and this was a team effort, and the ways in which it could be applied to learning about X, Y, and Z. And then some, I didn't really have that at all. It was really about the mechanics of what went into the project. So we had 55 students in this very first study, undergraduate students at 2 different universities, read this actual description from this NSF-funded project, but we changed a couple of the things, right? So I'll tell you the real one is the high communal value. We took one that was high in communal value, and we didn't just take that stuff out. We just made it less communal so they'd be equal in length. So here's what it looked like. I know you're not going to be able to see that, but this is a description of some engineering a project where at the end, where the little red arrow is really the only part that's different. There's a couple of sentences and words changed throughout, but it's the identical science. The science didn't change, but whether or not at the last pit they said these results might be useful for understanding how infants can help with mobility problems, and looking at infants with brain injury in particular, how this type of technology might be useful in those kinds of innovations in the future. So it's just adding this one sentence about the translational impact, essentially, of this work. And what we found was if we asked the students, okay, read this and tell me what you think. Do you think this type of research affords communal values? Are you interested in doing this kind of research? Would you want to sign up with the professor who did this research? Would you might want to work in his lab someday? And how positive just in general about science are you? And here's what we found. Well, it was, this is our manipulation check. If we thought this was the communal value description, it in fact was, so that's good. So they rated the one that had the infant information as more communal. And if they had this communal description, this one sentence at the very end, the science didn't change, right? It was just the possible applied value at the very, very end. This perception of communal affordance predicts positively their future motivation to think about a scientific career and be involved in research. So this very simple little addition significantly changes students' interest and future interest in pursuing science. So we also wanted to look at positivity, and the same type of pattern arrives. So they read this communal orientation value of doing this kind of science. They see the communal applied value of it, and then they're more positive just in general, positivity towards science and science research in general. So what we think is happening here is this really important sort of overall notion that if we can change people's stereotype of STEM, of the scientific researcher, to one that involves the reality, which is we do work in teams and we do collaborate, And we do very often have some way, shape, or form. There's some applied value or translational impact that we could make notable, that this actually enhances our students' motivation. And this is our path model to say when we put it all together, we also reran it controlling for agentic values, and the pattern still holds true. So above and beyond the prestige and the money and the power that's sort of associated with being a scientist, the communal value is still importantly predicting these important outcomes. So what's the take-home message from this particular study? And that was a pilot study, one in a big, long series, is that thinking that science research provides opportunities to fulfill communal goals is important for developing students' interest in pursuing scientific research. And that is, we're not just saying going into science. We didn't frame it that way. We said to do research, to add to research, discovery, and innovation. Are you interested in that? And it's particularly true. We're mostly focused on Native American students and Latino students with my collaborator at Cal State Long Beach. It's particularly true for underrepresented minority students and for women, but everybody seems to really benefit. So there's a positive increase. Nobody is harmed by adding this communal piece of information to our scientific endeavors. We have a combination of both experimental and those correlational studies, and of course, we really want to start looking at different stages of the pipeline. So we are focused right now mostly on the back half. Like, you've had to get pretty far if you're already working in a faculty member's lab. So we want to sort of back it up in time and start looking at different points. And we heard earlier somebody talking about, the importance of pre-kindergarten, right, preschool. So, why do we care about what worms are doing? How is that useful? Well, we can easily link that to a communal value. So our next step for our personal project is this next year we launch a huge intervention project to actually get these students who are undergraduate research assistants right now at 2 different universities to think about for themselves. You're washing dishes. All right, this is going to be tough. Okay, so you're washing dishes. In the scheme of things, how is your work in this lab, when primarily what you're doing is washing dishes, how might it be communal and help you feel connected to your lab mates and your team, and how might it have applied value? Well, for the most part right now, the students can't tell us. When we just ask them, talk about it, tell us what, in your lab experience, can you do this? And they're like, I can't. So they need help. And so what we say is, and this is what the intervention will be, is we're going to have those faculty mentors, those STEM faculty, help their students understand the impact and the possible translational nature of their work. And they're getting randomly assigned to do this or not. Because as a student, it can't be up to you to sort of draw that connection, because you only probably have a teeny tiny slice of that research project that you even have any clue what's going on, and you're really just, doing quantification and making out a notes and taking temperatures of something. You don't understand what the other 10 people in your lab are doing and how it sort of all comes together to see the big picture, but your faculty member does, because your faculty member probably wrote a grant. And anymore, your faculty member is not going to get funded if they don't at least have a little paragraph on the broader impact of their research, right? That's NSF speak, or the translational value of their research. So your faculty member needs to, I think, be willing to share that information with their students. And this, we think, from our preliminary data, is going to go a long way in engaging, catching, and holding onto student interest over time. So my suggestion for those, I know there was a lot of students that stood up when Kelly asked to recognize all of you hardworking undergraduate and graduate student researchers in the room. If you're unclear, ask your professor. Right? I hate to put the burden on the victim here, so to speak, but it's a great question. Raise your hand and say, in the scheme of things, I know I'm washing dishes, but why is, sort of tell me more about the overall project involved here. And we think that that's going to be key to securing student interest. How did my own student interest come about? So as Dr. Clevey mentioned, I did my own undergraduate research here at UCCS, the fine years of 1993 to 1997. And I started my path here at UCCS. I was the second cohort of freshman seminar. with Connie Staley, who is pictured here. You should recognize her because she looks exactly the same. She's right there in the middle there. And so this freshman seminar, for my experience, was incredibly formative because we got connected. You got connected very closely with this small group of students who became your, they were all from all different majors, but you had a cohort. And so often in college, our freshman class, you might be taking classes with all sorts of different people. You very rarely see the same 5 people throughout your day. So we don't have a sense of cohort like you might have had in high school. And you get that again in graduate school. You become a first-year student or a second-year student. So you sort of get that back. But between freshman and senior year in college, that's gone. Plus, people take 7 years to graduate, and you can't really ever predict somebody's course in there. So freshman seminar was really great for that. And the other thing that happened in my freshman year was I took Psych 100. Anybody in here take Psych 100 here at UCCS? Intro to Psychology? Just one person, right? If you've ever taken an Intro to Psych class, most universities, you get to be a research subject. Anybody ever been a research subject in a psych experiment? More people? All right. So part of that is to show students, because people hear I'm a psychologist and they think I help people. No, I don't help anybody. But I study people who want to help people. That's how I frame it anyway. But you get to be a research subject partly because the best way to learn about psychological science is to actually be a participant in a study, and you'll get to actually experience what it's like to how psychology does data gathering. So I was a research subject in my Intro to Psych class here, taught by Fred Coolidge, and I was interested. I could not sort of guess. I was really fascinated. Why did they make me look at those dots and push the keyboard? I don't understand. I still actually don't know why I did that study in particular, but I became a research subject. This was a graduate student in the program, and so I got really interested in psychology and had my own psychology research experiences, so I started shopping around. All right, I'm a psych major. I like these psych experiments. I'm going to start shopping around on the faculty and see what kinds of stuff they're doing. So I became a research assistant for quite a number of the faculty over time. I started with Dr. Sarah Qualls, and she had doing some coding, some qualitative coding of people's older adults' responses to some particular questions, and it didn't really I wasn't really fascinated by that, so that didn't last a whole lot. And then I started working with Dr. Chip Benight, who had studied the Oklahoma City bombing and sent in a team to collect a bunch of data on social support and coping mechanisms that happened. I was like, well, that's a little more interesting. I was very involved, but that data was already collected. It wasn't part of that at all. I just was helping to kind of decode the data. And then I met Kelly, Dr. Klebe, and I was starting to get interested in data, and so I talked with her about working with her on an honors project, and what sucked me in is she said I could collect my own data. And I was like, awesome, yes, I want to collect my own data. I don't want somebody else to give it to me. I want to collect my own. And we maintained that relationship, but while doing it, I sort of had a little affair. A research experience affair with a faculty member like 2 doors down from her, because he did research on thoughts of death and hot sauce aggression, and that sounds way more interesting. So I was like, I'm going to work in both labs. I know that you don't think I'm committed, but I mean, look at this list. Why wouldn't you want to go work in the thoughts of death and hot sauce lab? Like, that just sounds fun, right? And so this is where I found social psychology. So Kelly and I maintained our collaboration and my love for data, but this is how I want to answer research questions. Absolutely. And so my culture of psychological science as an undergraduate, remember, I'm an undergraduate here, right? So by the time, this was my junior year when I started working with Kelly and Tom pretty closely, and I essentially assimilated into a graduate student as an undergrad because I became connected with this very small group of students. I worked in various labs, and now I knew lots of the faculty, right? So it's also a good idea to go ahead and go 2 doors down and see what that faculty member is doing also, because you might find something more interesting, or you might go, no, I really still like this other project that I'm doing. So my culture of science, what is psychological science? The department was in the science building now. That's where psychology used to be housed. You should see that this is Tom Pazinski, the one dressed like death. He is still a faculty member here on sabbatical. This is Chuck Benight. He is also here with his he's still here, and his daughter's all grown up, but she's being held right there. And then this is Kelly and I on that infamous disgusting boiled peanuts trip. Like calamari. I mean, she was just trying to make me eat a bunch of yucky stuff, and I was from Colorado Springs. Blah. And so I started to get to go to, we had fun, right? So my notion of science and research was engaging. It was fun. We had a community within our sort of small group that I essentially crashed the party whenever I could. I also just want to end, before I take a few questions, with showing you some of my own research assistants and how I go about it. So this is a list of them, and I'll put some pictures up from time to time. The two with the blacked out was because they were Confederates, so they were actors in one of my studies, so we thought that was funny. I have had a consistently sort of small-ish group of a team of about 5 to 7 undergraduate students a year who are my research assistants, and this is my most current team. It's a smaller group, but we're a team, and we collaborate and we talk to each other, and I'm trying to do, they're only seeing one small piece. They might be the person entering data from some survey into a Excel spread file. They're not understanding where this data come from. So I try to spend time telling them about the data and why it's important and how they're contributing. So this is my very small team this particular semester. So thank you to my research assistants, and thank you to UCCS and the psychology department for tolerating me all of those years. And I'm happy to take some questions now. Or you can clap for me.